An object the size of Manhattan tears into our solar system at 130,000 miles per hour. This is 3I/Atlas, only the third confirmed interstellar visitor ever detected. But this isn't just another cosmic fragment drifting through the void. Leading astronomers are already debating signs of non-gravitational acceleration, a subtle deviation that hints at controlled propulsion. Now whispers circulate about a possibility even experts hesitate to voice aloud. Could 3I/Atlas be a nuclear-powered reconnaissance craft following a pattern so improbable that scientists claim it has less than a 0.005% chance of occurring randomly? If the premise sounds outlandish, consider what's at stake. The evidence surrounding 3I/Atlas will challenge everything you believe about what moves among the stars. The first clue lies concealed within the acceleration data. Precision becomes paramount when the stakes stretch across light years. The initial acceleration indicators for 3I/Atlas emerged not from wild conjecture, but from the relentless routine of astrometric measurement. Each night, observatory teams in Chile and Hawaii logged the object position against a backdrop of reference stars, recording timestamps accurate to the second. The Atlas telescope CCD arrays, calibrated against field standards, captured faint streaks of light as 3I/Atlas swept across the sky. These raw images, paired with Pan-STARRS follow-ups and Hubble's pinpoint snapshots, formed the foundation of the official dataset submitted to the Minor Planet Center. From these thousands of data points, astronomers constructed a detailed ephemeris, a map of predicted positions hour by hour for the weeks following discovery. The process hinges on residuals, the difference between where the object should appear according to a pure gravity model and where it actually materialized. Each residual, measured in fractions of an arcsecond, serves as a test of the laws governing celestial motion. If something is pushing or pulling the object besides gravity, it will manifest as a pattern in these numbers, a drift, a kink, a systematic offset that grows over time. No persistent deviation emerged. No unexplained acceleration at the millimeter per second squared level rose above the noise. The official orbit solution from JPL's Horizon system and the Minor Planet Center matched the observed track without invoking any non-gravitational terms. Adding a hypothetical thrust or jet parameter did not improve the fit. The data thus far aligned with a natural, gravity-driven trajectory. Technicians and analysts, some working through the night, cross-checked calibration files and error bars. They examined astrometric charts, overlaying predicted and observed paths, searching for hidden structure in the scatter. Each outlier underwent scrutiny. Was it a cosmic ray hit? A background star? A tracking glitch? Only after exhaustive review did the final residual plots confirm that the motion of 3I/Atlas could be explained by the known gravitational influences of the Sun and planets alone. Still, the process never truly ends. As new data arrive from space-based telescopes and as the object arcs closer to the Sun, every fresh measurement runs through the same battery of statistical tests. The margin for error shrinks with each additional night, and the search for subtle thrust-like behavior continues. For now, the evidence for a propulsion signature is not merely weak. It is absent. But in the realm of interstellar mysteries, the next observation could always rewrite the entire story. The debate over what drives 3I/Atlas splits the astronomical community along a familiar fault line. One camp points to the classic physics of comets. Volatile ices heated by the sun, erupting into asymmetric jets that nudge the nucleus ever so slightly off course. In this interpretation, every non-gravitational twitch can be traced to a pocket of carbon dioxide bursting free, sending a faint plume into space. The numbers support this view. For a comet of this size, even a jet releasing just a few kilograms of gas per second could account for millimeter per second squared accelerations, if they existed. Yet the most recent photometry and spectroscopic data show no strong evidence of such outgassing. The coma is present, but jets remain unresolved, and the tail's structure matches what would be expected from sunlight-driven activity, not from directed propulsion. On the opposing side, a handful of theorists led by Avi Loeb argue that the absence of clear outgassing, combined with the object's brightness and trajectory, leaves the door open to more radical explanations. Loeb has publicly floated the possibility of a nuclear-powered propulsion system, suggesting that if 3I/Atlas were an engineered probe, a gigawatt-class reactor could produce the kind of acceleration and luminosity observed, at least in theory. He points to the object's planned planetary flybys and the statistical rarity of its path as circumstantial evidence for intent. The calculations are bold. A gigawatt reactor would generate thrust on the order of 1,000 newtons, enough to noticeably alter trajectory over weeks or months. But such a system would also emit intense gamma rays, neutrons, and heat, all of which would be detectable by Earth-based and space-based observatories. NASA and most cometary scientists remain skeptical. They counter that no gamma, neutron, or infrared excess has been detected at the position of 3I/Atlas, not by Fermi, Swift, or NuSTAR, nor by ground-based radio arrays. The object's visible and infrared brightness matches what would be expected from sunlight reflected off dust and ice, not from an onboard power source. Detailed modeling shows that a nuclear drive of the scale required would outshine the comet in thermal and high-energy bands by orders of magnitude. The absence of these signatures, they argue, constitutes strong evidence against an artificial engine. The conversation grows more complicated when considering the limits of current observations. The coma and tail, while faint, could mask small jets below the resolution of available telescopes. Polarimetric and thermal infrared data, still pending from the James Webb Space Telescope and the Very Large Telescope, may eventually provide a more definitive answer. For now, the evidence tilts toward natural explanations, but the possibility of something engineered lingers in the background, fueled by the object's statistical oddities and the lack of a perfect fit to standard comet models. As Loeb frames it, extraordinary claims require extraordinary evidence. But until we have that evidence, we should keep an open mind. Meanwhile, NASA's lead comet scientist offers a measure of rebuttal. What we see is consistent with a highly active yet natural interstellar comet. We'll keep looking, but the case for a nuclear engine just isn't there. With each new data release, the debate sharpens. The question persists: are we witnessing the slow, uneven push of ancient ice, or the deliberate thrust of something built far from home? The answer, for now, is written in the faint jets and silent spectra of a visitor racing through our solar system. The numbers alone barely hint at the reality. Astronomers estimate 3I/Atlas spans nearly 20 kilometers from end to end, an object of the bulk and breadth of Manhattan Island, but hurtling through space at more than 130,000 miles per hour. Imagine the entire grid of city streets, skyscrapers, and riverside parks not anchored to Earth, but sweeping across the void, indifferent to planets and orbits. This is not a pebble or a snowball. This is a city-sized mass, its presence so vast that even the most sensitive telescopes struggle to pin down its true outline. Photometric analysis provides the first clues to its scale. When sunlight strikes the icy surface and scattered dust, a fraction reflects back toward Earth. By measuring that faint glimmer, astronomers reverse engineer the likely diameter. Even with generous margins for error, uncertainties in albedo, dust coverage, and coma brightness, the lower bound remains staggering, at least 15 kilometers across, possibly more. If you could set 3I/Atlas down beside Manhattan, its shadow would swallow the borough whole, stretching from Battery Park to Harlem, its mass dwarfing every structure built by human hands. Yet for all its size, 3I/Atlas arrived as a near ghost. The reason lies in the darkness between stars and the limitations of even our best sky surveys. Its approach vector placed it near the sun's glare, a region where ground-based telescopes are nearly blind. Atlas and Pan-STARRS, the automated sentinels scanning for dangerous asteroids, caught the first hints only when the object had already crossed into the inner solar system. Early images showed not a sharp-edged rock, but a blurred, swelling glow, a coma of dust and gas that masked the nucleus, making direct measurement a challenge. Only by stripping away the coma's contribution, pixel by pixel, could teams estimate the hidden core's true extent. The sheer scale of 3I/Atlas forces a reckoning with our place in the cosmos. This is not an outlier among comets. It is an outlier among outliers. Both Oumuamua and Borisov, the only other known interstellar visitors, were tiny by comparison. One barely the length of a football field, the other a modest mountain. 3I/Atlas, by contrast, brings the mass of a small city, its kinetic energy beyond anything delivered by an asteroid in recorded history. If such an object were to strike a planet, the consequences would be unthinkable. But this one is just passing through, indifferent to our worries, following a path set in motion before the rise of civilization. Detection, then, is a matter of both luck and vigilance. The object size made it brighter than it might otherwise have been, but its trajectory, nearly aligned with the ecliptic yet retrograde, kept it hidden until the last moment. Only the coordinated efforts of global observatories working in concert managed to catch and track this interstellar wanderer as it swept past. In the end, the scale of 3I/Atlas is not just a number on a chart. It is a reminder that the universe still holds surprises vast enough to challenge our imagination, and that even the largest visitors can arrive in silence, leaving us to wonder what else might be crossing the darkness unseen. A hyperbolic orbit is nature's signature for an interstellar traveler. Unlike the looping ellipses of planets and comets bound to the sun, a hyperbola is an open path, one that never closes, never repeats, and never returns. For 3I/Atlas, the numbers are unambiguous. Its orbital eccentricity exceeds 1.00005, a mathematical guarantee that it is not a child of our solar system, but a visitor from the deep beyond. This object entered the solar system at nearly 61 kilometers per second, about 137,000 miles per hour relative to the sun. That speed alone would punch it past the solar escape threshold, even if it had arrived empty-handed with no help from gravity or jets. The defining feature of a hyperbolic escape is its finality. Once 3I/Atlas completes its arc around the sun, it will not linger. There is no gravitational leash to pull it back, no orbit to retrace. Its outbound velocity, even after accounting for the sun's pull and any planetary tugs, remains positive, an astronomical one-way ticket. Astronomers calculate its excess velocity, or V-infinity, as approximately 26 kilometers per second when it finally leaves the solar system's sphere of influence. That's more than enough to clear the Oort cloud and vanish into interstellar darkness. To visualize this, imagine tracing the object's path on a map of the solar system. Instead of an oval or a looping curve, the trajectory slices through the planetary orbits like a spear. The sun's gravity bends the path, but cannot capture it. Even Jupiter, the solar system's heavyweight, can only nudge the course, not bind it. The result is a fleeting opportunity. 3I/Atlas will spend just months inside the orbit of Mars, and only a handful of weeks near Earth's distance from the sun. After that, it accelerates outward, its path forever diverging from the sun's embrace. This unbound status is more than a technicality. It defines the urgency of the scientific response. Every observation, every spectrum, every image must be captured before the window closes. There will be no second chance. The same orbital mechanics that prove 3I/Atlas is not from here also guarantee it will never pass this way again. For astronomers, this is both a challenge and a call to action. The clock is ticking, and the data collected in these brief months will shape our understanding of interstellar visitors for decades to come. The hyperbolic escape also sets the stage for a deeper mystery. If this object is following a path that brings it close to multiple planets in quick succession, is that the result of pure chance or something more deliberate? The next chapter in the story will track how 3I/Atlas threads a needle, passing by Mars, Earth, Venus, and Jupiter in a sequence so rare as spark debate about intent, probability, and what it means to be watched from afar. The trajectory of 3I/Atlas reads like a cosmic itinerary, planet by planet. Each encounter logged with precision, a mission plan. On September 30th, 2025, it passes within 13.9 million kilometers of Mars, close enough for orbiters to track its coma as it slips past a red planet. Just 2 weeks later, on October 14th, the object's path brings it to a near-Earth pass, skimming by at a distance of 27.5 million kilometers. Far outside the moon's orbit, certainly, but closer than any interstellar visitor ever recorded. Venus comes next on November 2nd, with a flyby at 27.2 million kilometers. Then, as winter deepens in the northern hemisphere, 3I/Atlas swings out toward Jupiter, reaching its closest approach to the gas giant on March 8, 2026, at a scant 22.4 million kilometers. Each of these milestones is tracked not just in kilometers, but in days and hours, each one a fleeting observational window that will never repeat. The sequence is not random. The object's hyperbolic path, nearly planar to the ecliptic, but running in reverse, threads a narrow corridor through the inner solar system. Orbital analysts plot the ephemeris, noting how the trajectory grazes the gravitational spheres of 4 planets in succession. The odds of such a tour happening by chance, according to published simulation studies, are less than 0.005%, a figure that has fueled both scientific curiosity and public speculation. This pattern, mapped out in advance by the world's best telescopes and refined with every new data point, invites close scrutiny. The flybys are not grazing impacts, but measured passes, close enough to enable detailed study, distant enough to avoid capture or collision. For planetary scientists, each approach offers a unique vantage. Mars orbiters scan for dust outbursts. Earth-based arrays chase the coma's evolution. Venus flyby geometry challenges infrared imaging, and Jupiter's immense gravity provides a final test of the object's outbound arc. The choreography is striking. No other interstellar object has traced such a sequence through our planetary neighborhood. For some, the alignment hints at reconnaissance, a deliberate pattern optimized for observation while minimizing the risk of detection. For others, it is a statistical outlier, a rare but natural trajectory produced by the random dance of galactic debris. What is certain is that the path of 3I/Atlas, mapped in millions of kilometers and marked by planetary encounters, stands as one of the most improbable tours ever recorded in the history of solar system astronomy. Avi Loeb's argument gains its sharpest edge not from the object's speed or size, but from the way 3I/Atlas threads the solar system with what appears on paper like tactical intent. The flyby sequence, Mars, Earth, Venus, Jupiter, isn't just rare, it's geometrically efficient. Each pass occurs at a distance close enough to enable high-resolution imaging of the planets, yet always far enough to avoid gravitational capture or collision. The object's trajectory hugs the ecliptic, nearly matching the plane of planetary orbits, but runs in the opposite direction, retrograde, offering line-of-sight access to each world without the masking effects of solar glare or planetary shadow. Consider the observational advantages. As 3I/Atlas sweeps past Mars on September 30th, the red planet sits almost perfectly illuminated, its thin atmosphere and surface features exposed to any passing sensor. 2 weeks later, Earth is positioned for a near-side view, with the object's path bringing it closer than any previous interstellar visitor, yet still outside the reach of our atmosphere's interference. Venus follows, with its cloud tops reflecting sunlight at a phase angle that maximizes contrast for remote imaging. By the time Jupiter enters the frame in March 2026, the giant planet's swirling storms and magnetic fields stand ready for scrutiny from a vantage point rarely granted to natural comets. Loeb points to these alignments as more than coincidence. He invokes the logic of reconnaissance. A probe sent to survey a planetary system would, in theory, optimize its path for maximum coverage with minimum risk. The geometry here is striking. Each approach is timed to exploit the best viewing angles, while the outbound leg ensures a clean escape into interstellar space. The odds of such a tour happening by random chance, he claims, are less than 1 in 20,000. That number, drawn from Monte Carlo simulations of random interstellar entries, is not universally accepted, but it carries rhetorical power. If the path is engineered, it reflects a level of planning that rivals our own planetary flybys. Skeptics counter that the solar system is a crowded place, and that with enough objects, even rare alignments will eventually occur. But the multi-planet sequence, combined with the object's hyperbolic retrograde trajectory, remains a statistical outlier. The question is not just whether 3I/Atlas is an artifact, but whether its path is optimized for observation in a way that natural dynamics alone struggle to explain. As the debate unfolds, the geometry of this encounter stands as both a challenge and an invitation to weigh the possibility of design against the long odds of cosmic chance. Each pass of 3I/Atlas through the solar system raises an unsettling question. Is this just cosmic chance, or does the trajectory hint at intent? Its path, skimming Mars, Earth, Venus, Jupiter, resembles a survey more than a random drift. Here, the dark forest hypothesis, once confined to science fiction and SETI debates, finds new gravity. The theory imagines a universe as a silent, dangerous place where survival depends on remaining unseen. Any civilization that reveals itself risks destruction. If an intelligence wanted to observe without being noticed, it might send probes that gather data from multiple worlds, then slip away quietly, leaving no trace but questions. Avilobe, known for challenging orthodoxy, draws a straight line from 3I/Atlas back to Oumuamua. In 2017, Oumuamua's odd shape and unexplained acceleration set off a storm of speculation about artificial origins. It was small, barely the length of a football field, and passed through without a sound, sparking more debate than answers. Now, less than a decade later, 3I/Atlas appears, 20 times larger, threading a path to the solar system with remarkable precision. The 8-year gap between these visitors is striking. Loeb suggests this timing may not be random, but the sign of a sequence, a scout, then a more capable probe, each pass testing for signs of life, each encounter watching for a response. The stakes stretch far beyond astronomy. If 3I/Atlas is more than a comet, if it is a messenger or a watcher, the implications reach into existential risk. SETI groups and security analysts have quietly debated whether to respond or stay silent. Meeting notes, though rarely public, reveal a community split between curiosity and caution. The dark forest logic urges silence. In a universe where every civilization is both hunter and hunted, discretion might be the only safety. Yet the urge to reach out persists. Loeb frames it simply. If it turns out to be technological, it would obviously have a big impact on the future of humanity. We have to decide how to respond to that. Each interstellar visitor becomes a test of our hopes and fears, a reminder that in the vast dark, every light could be both invitation and warning. Spectra and imaging from the world's leading telescopes reveal a story written in gas and dust. When 3I/Atlas first entered the solar system's outer reaches, its coma, an envelope of gas and dust, was already visible, glowing faintly against the black. This activity, detected at a distance where sunlight is weak and most comets remain dormant, drew immediate attention. Analysis of the coma's composition, using data from ground-based observatories and early JWST spectra, points to an unusual chemical fingerprint. Carbon dioxide dominates, with CO2-to-water ratio measured at nearly 8-to-1. For comparison, most solar system comets display the opposite pattern, with water-ice leading the mix. Here, the chemistry suggests a nucleus forged in a colder, perhaps more distant region of another star's planetary system, where carbon dioxide ice could survive for billions of years. The coma's structure and brightness offer further clues. Photometric models, which estimate the object's reflectivity or albedo, must account for the scattering of sunlight by dust grains. Early results place 3I/Atlas among the brighter comets observed at similar distances, but not outside the bounds set by known icy bodies. The albedo remains uncertain, with estimates ranging widely due to unresolved dust and the challenge of separating the nucleus from its shroud. Still, the observed brightness aligns with expectations for a large, active comet, not an engineered reflector or artificial shell. Imaging campaigns led by NASA's cometary scientists track the evolution of the coma and tail. The tail, extending millions of kilometers, displays a classic anti-solar orientation, pointing away from the sun as radiation pressure pushes dust outward. No evidence of persistent collimated jets or unnatural emission lines appears in the data so far. The high standoff distance during Earth's closest approach, over 167 million kilometers, means that even the most sensitive instruments struggle to resolve fine details. But the broad features match what expected from sunlight-driven sublimation and dust release. Skeptics in the planetary science community point to these signatures as strong evidence for a natural origin. The coma's chemical makeup, the photometric trends, and the lack of high-energy emissions all fit the profile of an interstellar comet, albeit one with peculiar history. As more data arrive from ongoing campaigns, scientists continue to probe for anomalies, unusual polarization, thermal excess, or spectral lines that could hint at something engineered. For now, the balance of evidence weighs heavily on the side of cometary physics. The challenge is to capture every photon, every spectrum, before 3I/Atlas slips back into interstellar darkness, taking its secrets with it. Interstellar visitors like 3I/Atlas don't just challenge astronomers. They provoke engineers to ask how close humanity can come to catching up. Within days of the object discovery, mission planners at NASA, ESA, and private think tanks dusted off rapid intercept studies and ran the numbers. The results are sobering. To match a hyperbolic trajectory moving at 61 kilometers per second, over 130,000 miles per hour, any intercept mission would need to deliver a probe on a one-way sprint, burning through the solar system at record-breaking speeds. Project Lyra, a collaboration of propulsion specialists and mission designers, has spent years modeling what it would take to chase interstellar objects. Their calculations show that for 3I/Atlas, a direct chemical rocket launch from Earth is out of the question. Even the most powerful boosters, SLS Starship, Ariane 6, fall short of the required delta V, the change in velocity needed to catch the target. The only viable option on paper is a solar orbit maneuver. Launch a probe toward Jupiter, swing it back for a hair-raising dive near the Sun, and ignite the engines at perihelion, where gravity multiplies every ounce of thrust. This sequence, first proposed for Oumuamua, squeezes the most energy from each kilogram of propellant, but demands technology that sits on the edge of what has ever flown. The mission window is brutally tight. By the time 3I/Atlas was identified as interstellar, months had already slipped away. Lyra's delta-V chart showed that every week of delay adds kilometers per second to the requirement, shrinking the feasible payload from a refrigerator to a suitcase, and then to a shoebox. Launch windows for a solar orbit intercept close by early 2026. After that, the object races too far, too fast for any plausible mission to catch up. Even the most aggressive plans, solar thermal rockets, advanced electric propulsion, miniaturized science packages, struggle to meet the schedule. ESA's Comet Interceptor, a pre-launch spacecraft waiting at L2 for a suitable target, offers a glimpse of a different strategy. Built to pounce on long-period comets, it was never designed for the speeds or trajectory of an interstellar visitor like 3I/Atlas. Yet its philosophy, prepare in advance, remain flexible, and strike when opportunity appears, has become the new rallying cry among planetary defense engineers. The lesson is clear. To meet the next interstellar arrival, readiness must be the rule, not the exception. Mission kits must be prepositioned, propulsion stages tested, and launch protocols streamlined. The clock starts ticking the moment an object is detected, and every hour lost is a kilometer per second harder to recover. For 3I/Atlas, the engineering challenge is not just a race against celestial mechanics. It is a test of how quickly science can turn urgency into action. On one side, researchers point to decades of silence in the cosmic radio background. No confirmed signals, no evidence of galactic conversation. They invoke the dark forest hypothesis, warning that in a universe where every civilization is a potential hunter, even a whisper could be fatal. Others see the arrival of 3I/Atlas as a fleeting chance to make contact, to announce our presence, or at least test the waters. If this is a probe, it may already know we are here. No consensus emerges. The debate is unresolved, and the window for action is closing. Each side cites the same facts: the rare trajectory, the absence of direct evidence for intent, the specter of cosmic risk, but draws opposite conclusions about what those facts demand. In the end, the question lingers. In the face of the unknown, is it wiser to speak or to listen? The stakes are measured not just in data, but in the future we choose for ourselves. As of September 2025, critical data remains limited, and some details are classified. Whether 3I/Atlas is a natural wanderer or something more, its arrival challenges humanity to prepare, observe, and respond to the best science we have. The object continues its journey through our solar system, each day bringing new observations and new questions. Ground-based telescopes track its path. Space-based instruments probe its composition. Mission planners debate whether humanity should reach out or remain silent. For now, 3I/Atlas keeps its secrets. It moves through the darkness between worlds, a Manhattan-sized enigma that arrived without warning and will depart without ceremony. Whether it carries the frozen remnants of another star's planetary system or something far stranger, one truth remains. We are being reminded, in the most dramatic way possible, that we are not alone in watching the cosmos. The universe is watching back. The call came to Dr. Sarah Chen's phone at an hour reserved for emergencies. On the other end, a trembling voice from the Deep Space Network facility in Goldstone, California. We're picking up something. You need to see this now. 20 minutes later, Chen stood in the operations center, coffee forgotten in her hand, staring at a waterfall display that showed something impossible, a narrowband radio signal, precisely at 1,420 megahertz, the hydrogen line, the universal frequency that any technological civilization would monitor, pulsing from the exact coordinates of 3I/Atlas. How long has this been transmitting? She asked, her voice steadier than she felt. 17 minutes. It started when the object crossed 25 million kilometers from Earth. We confirmed it with Arecibo's successor array and the Chinese Fast Telescope. It's real, Sarah, and it's modulated. The pattern wasn't random noise or natural emission. It carried structure, repetition, mathematical elegance. Prime numbers in the first sequence, then Fibonacci, then something that looked disturbingly like a coordinate system, possibly stellar positions. The signal strength was increasing as 3I/Atlas continued its approach, as if whatever was transmitting wanted to ensure we couldn't miss it. Within hours, every major observatory on Earth had turned toward the visitor. The James Webb Space Telescope interrupted its observation schedule. Military satellites repositioned. The signal remained constant, unwavering, undeniable. After 8 years of speculation about Oumuamua, after months of debate about natural versus artificial origins, 3I/Atlas had answered the question itself. We were not alone, and something out there wanted us to know it. The leak was inevitable. By dawn, amateur radio astronomers had detected the signal independently. By noon, it was trending worldwide. Governments scrambled to coordinate a response, but the internet had already made that impossible. Humanity, in all its chaotic glory, was shouting into void in 1,000 different languages. At the United Nations, an emergency session convened. Should we respond? Could we stop individual nations, or even private citizens, from responding if we wanted to? The Dark Forest advocates pleaded for silence, invoking the possibility that we were announcing our presence to a hostile force. Others argued that if 3I/Atlas had found us, remaining silent was pointless. The probe already knew exactly where we were and what we were. Avi Loeb appeared on every news channel, vindicated yet visibly shaken. I've spent years arguing that we should take the possibility of extraterrestrial technology seriously, he told one interviewer. Now that we have it, I'm not sure we're ready. But ready or not, first contact is happening right now, whether we like it or not. The signal continued, unwavering. Analysis teams worldwide worked to decode its meaning. Was it greeting? A warning? A test to see if we were intelligent enough to respond? The mathematics embedded in the transmission suggested a level of technological sophistication that made our most advanced systems look primitive. Yet there was something almost patient about it, as if whoever sent this probe had done it before many times and knew exactly how a young civilization would react. October 29th, 2025. The second revelation came not from radio telescopes, but from an infrared observatory in Hawaii. 3I/Atlas was changing. The coma that had surrounded the object since its discovery was dissipating, not gradually, as would be expected from natural outgassing, but systematically, section by section, as if being vented deliberately. Beneath the veil of dust and ice, something was emerging. High-resolution adaptive optics images showed what had been hidden all along. The nucleus wasn't an irregular chunk of ice and rock. It was geometric, faceted. The thermal signature showed heat distribution patterns that couldn't be explained by solar radiation alone. Internal systems were active, had been active all along, carefully masked beneath a natural-looking exterior. It's been camouflaged, whispered Dr. Chun, studying the images. The entire approach, the coma, the tail, it was designed to make us think we were looking at a comet. But now that it's signaling, it doesn't need the disguise anymore. The object's true structure defied easy description. The best images showed a dark, angular core approximately 18 kilometers long, covering what appeared to be hexagonal panels or tiles. Some reflected sunlight with unnatural precision. Others absorbed it completely, creating patterns of light and shadow that hurt to look at, as if the geometry itself was wrong somehow. And then the object did something that sent shockwaves to the scientific community. It adjusted its trajectory. Not much, just a fraction of a degree, a subtle course correction that would have been invisible except for precision tracking systems watching its every move. The change required thrust, deliberate acceleration, the very thing that had been debated and searched for since discovery. Now it was undeniable. 3I/Atlas wasn't falling through the solar system. It was flying. The new trajectory would bring it even closer to Earth than originally calculated. Not dangerously close, but close enough for every telescope on the planet to get a perfect view. Close enough that even amateur astronomers with backyard equipment could see it. Close enough to ensure that every human with eyes could witness what was happening. Whatever 3I/Atlas was, whatever intelligence had built it and sent it on this journey, it wanted an audience. November 1st, 2025. The signal changed. For days, cryptographers, mathematicians, and linguists have been attempting to decode the transmission. The mathematics were clear enough. Universal constants, geometric proofs, physical laws that any technological civilization would recognize. But the deeper meaning remained elusive. Then, at precisely 12 o'clock Universal Time Coordinated, the signal shifted to a new pattern. This one was different, more complex, more biological. It's DNA, gasped a biochemist at MIT, staring at her screen. The signal is encoding genetic sequences. Not ours, but the structure is the same. For bases, arranged in codons, exactly like terrestrial life. The implications hit like a physical blow. Either life's fundamental chemistry was universal, the same across light years and unrelated origins, or something far more unsettling was true. The signal continued, spooling out genetic information for organisms that had never evolved on Earth. Strange proteins, alien metabolic pathways, the biochemical blueprints for life that had emerged under a different sun. But why send this? What did it mean? The answer came from an unexpected source, a graduate student in astrobiology who'd been working through the night. It's not just random sequences, she announced to her exhausted team. There's structure to what's being transmitted. It's a family tree, an evolutionary history. They're showing us where they came from. The genetic data told a story billions of years old. Life emerging on a world very different from Earth. Evolution taking paths both alien and somehow familiar. Intelligence arising, technology developing, and then something else. The sequences showed deliberate modification, artificial changes. This civilization hadn't just evolved. It had engineered itself, rewriting its own genetic code, adapting to survive in the void between stars. And at the end of the transmission, one final sequence. This one was different from all the others. Simpler, more recent. It took 3 more hours before anyone understood what they were looking at. It's a human genome, Dr. Chen said quietly. They've been scanning us, learning about us. The whole time they've been here, 3I/Atlas hasn't just been observing our planets. It's been studying us. November 3rd, 2025. Earth's closest approach to 3I/Atlas, now just 23 million kilometers away. The object dominated the sky, visible even in daylight. A bright point that didn't twinkle like a star. Every telescope, every camera, every eye on Earth turned upward. Humanity held its breath. The signal had become more complex, more insistent. It was clear now that 3I/Atlas was trying to communicate something specific. But the message remained frustratingly incomplete, as if waiting for something, as if waiting for us. Then someone made the connection. The signal's pattern, its repetitive structure. It wasn't a statement. It was a question. A physicist in Tokyo was the first to articulate it. It's asking if we're ready. That's what all of this is. The mathematical proofs, the genetic data, the display of technological capability. It's a test. They're asking if we're developed enough, mature enough for what comes next. But ready for what? First contact? An invitation to join some galactic community? Or something darker, more final? The Dark Forest theorist's warnings echoed in everyone's minds. Perhaps this was how it happened. Perhaps civilizations that passed the test survived, and those that failed, the decision couldn't be delayed any longer. Humanity had to respond. But with what? What could we possibly say that would demonstrate our worth, our readiness, our right to continue existing? Different groups proposed different messages. Mathematical proofs to show our intelligence. Cultural achievements to demonstrate our creativity. Peace declarations to prove we'd move beyond violence. Religious texts. Scientific discoveries. Music. Art. Poetry. Everything that made us human. In the end, the response that Earth transmitted wasn't crafted by governments or decided by committee. It was assembled from thousands of individual messages sent by people around the world. Scientists and artists, children and elders, believers and skeptics. A chaotic, beautiful, contradictory chorus of human voices, saying in essence, we're here, we're aware, we're trying to understand. We're not perfect, but we're learning. The transmission lasted for 6 hours, beamed toward 3i/Atlas on the same frequency it had used to contact us. Then silence. Waiting. November 5th, 2025. 2:33 Universal Time Coordinated. 3i/Atlas responded. The signal that had been constant for days suddenly ceased. In its place came something different, a burst transmission, lasting only seconds, containing more data than all previous communications combined. Supercomputers around the world began the work of decoding it, but even the preliminary analysis showed something astonishing. It was a star map, not of our region of space, but of the entire galaxy. Thousands of stellar coordinates, each one marked, each one tagged with data. And beside many of those coordinates, not all, but many, a symbol that could only mean one thing: life, intelligence, civilization. We were not alone. We had never been alone. The galaxy was full of voices, full of minds, full of beings who had looked up at their own skies and wondered the same questions we were asking now. But there was more. Some coordinates were marked differently, darker, final. These were the civilizations that had failed the test, or perhaps had made the wrong choice, had shouted too loudly into the dark, had revealed themselves before they were ready. And our own sun, our own soul? It was marked now, flagged as occupied, noted as observed. But the classification beside it remained incomplete, open, as if our story was still being written, our fate still undecided. 3i/Atlas began to accelerate, not with the slow push of outgassing or the subtle nudge of solar pressure, but with purpose and power. Whatever propulsion system it possessed, nuclear, antimatter, something else entirely, it was no longer hiding. The object's velocity climbed steadily as it began its long fall away from the sun, back toward the darkness between stars. One final transmission came as it crossed the orbit of Mars. This one was simpler than the others, but somehow more profound. Mathematical patterns that, when visualized, formed images. The first showed 3i/Atlas itself, traveling between stars. The second showed many objects like it, hundreds or thousands, fanning out from some origin point too distant to identify. The third image showed Earth, our moon, our blue world hanging in the black. And then, surprisingly, showed again in the future, still there, still alive, still orbited by what might be ships of our own design, traveling outward. The interpretation was debated, but the message seemed clear enough. You've been judged. You've been found adequate. Not perfect, but adequate. You'll be allowed to continue. Perhaps, someday, you'll join us out here in the dark. Then 3i/Atlas was gone, accelerating on a trajectory that would take it out of the solar system within months. The object signal faded to nothing. The sky returned to normal. The extraordinary visitor became just another point of light, then a memory, then a legend. But Earth was changed forever.